Welcome to lecture on mathematical modeling. In this lecture, we will discuss few numerical problems. In which we will use the impedance method to write the differential equations, write the equations in complex frequency domain or to obtain the transfer function. So far we have written the differential equation, then we have taken the Laplace transform and we obtain the transfer function. We don't need to write the differential equation. Using the impedance method, we can directly write the transfer functions. So we will understand this with the help of few examples. So first example we will take for a mechanical translational system. So we know that in a mechanical translational system we have three components. One is mass, then there is damper, and then there is a spring. So here we know that for mass there is force Ft equal to m into d square, if this is xt by dt square. So we take Laplace transform Fs equal to ms square into xs with initial conditions 0. So the impedance is defined as Fs by xs, that is equal to ms square. Similarly, for a damper, the damper force is C dx by dt, and when we take Laplace transform, it is C as xs. So impedance is Fs by xs, and that is equal to Cs. For a spring force is k into xt. We take the Laplace transform, we will find Fs equal to k into xs. So here the impedance is Fs by xs, that is k. So these are the impedances of the mechanical elements: mass, damper and spring. So now we take the example. So we take this first example, first problem, write the equations of motion in S domain. So we want to write for this system the equations of motion in complex frequency domain. Once we are able to write the equations in complex frequency domain, we can obtain the transfer function of that system. So here we are going to directly write the equations using the impedance method. So this system is something like this. So here we have a spring and there is a mass. Then there is another spring, there is another mass, and on these there is one more mass. So here is another mass, and these are two masses. This is M1, M2, this is K1, K2, this is M3. The damping between, so this surface is C1 and damping here is C2. Here is C3, between these two blocks there is damping C3, and here is C4. So we apply a force Ft here. Now we assume that this system motion x1t, x2t and x3t So now we have to write the equations of motion for this system using impedance method. So we can have for mass m1, so sum of impedances connected to the motion of m1 into x1s minus sum of impedances between m1 and m2 into x2s minus sum of impedances between m1 and m3 into x3s equal to sum of applied forces at m1. So now sum of impedances connected to the motion of m1. So this is m1 and the m1 is getting impedance due to this spring, this damper C1. So C1 is equivalent viscous damping that is coming friction from this surface, and so we can write it. So this mass impedance m1 s square, because the mass has the impedance ms square. Here we have C1 and C3 into S K1 and K2. This is the impedance due to these two springs into X1S minus sum of impedances between M1 and M2. So between M1 and M2 there is impedance only due to spring K2 that is connecting these two masses. So minus K2 into X2S minus sum of impedance between M1 and M3. So between M1 and M3 there is C3. So minus C3S into X3S equal to sum of applied forces at M1. So M1 is not subjected to any force, so this is 0. So this is equation number 1. Similarly, for mass M2, we can write here M2 and then sum of impedances connected to the motion of M2 into X2S minus sum of impedances between M1 and M2 into X1S minus sum of impedances between M2 and M3 into X3S equal to sum of applied forces at M2. So, if we apply these for this mass, so sum of impedance connected to the motion of M2. So, here is K2, C2 and C4, and the impedance of this mass M2 S square. So, this is M2 S square plus C2 plus C4 S plus K2 and X2S minus sum of impedance between M1 and M2 is K2. So, K2 into X1S minus sum of impedance between M2 and M3. So, M2 and M3 is C4. So, it is C4 S X3 S, that is equal to sum of applied forces at M2. So, here M2 is subjected to a force Ft, and here we have to take the Laplace transform of Ft. So, we write Fs. This is equation number 2. Similarly, for mass M3, so here motion of M3 into X3 minus sum of impedances between M1 and M3 into X1S minus sum of impedances between M2 and M3 and X2S and sum of applied forces at M3. So, here sum of impedances connected to the motion of M3. So, they are the M3S square plus C3 plus C4 S X3 minus sum of impedance between X1 and between M1 and M3. So, between M1 and M3 is C3. So, C3S into X1S minus here between M2 and M3 is C4S into X2S, and that is equal to, there is no any force applied here. So, it is equal to 0. This is equation number 3. So, we can see that using the impedance method, we are able to write the equation of motion in S domain, complex frequency domain, directly and very easily. And these three equations are like this form. So, A11 x1 plus A12 x2 plus A13 x3 equal to B1, and this is A21 x1 plus A22 x2 plus A23 x3 equal to B2, and here A31 x1 plus A33 x2 plus A33 x3 equal to B3. So these equations, because here x1, x2 and x3 are these three variables and these terms are B1, B2, B3. So 0, Fs and 0. Now we can form a matrix delta of A11, A12, A13, A21, A22, A23, A31, A32, A33. This is delta. So we can use the Kramer's rule to find the transfer function. Whether we are interested to find the transfer function that is x3s upon fs or x2s upon fs or x1s upon fs. So we can find this transfer function. So for example, if we want to find here this x1, so x1 equal to this first column we have to replace with b1, b2, b3, b1, b2, b3, and these terms will be as such a12, a22 and a32, a12, a23, a33 upon delta. So we can find here x1 equal to this determinant upon this determinant, and we will get the, so we can get x1 as, and here is b1, b2, b3, so there will be fs also coming from this, and so we can find x1s by fs. So the transfer functions. So all these transfer functions we can find using these three equations. Now we take another example that is based on some electrical circuit. So we have another problem based on electrical circuit. So we have this example. So we can see here this example. We have this voltage source, resistance R1, R2, inductor L and capacitor C, and there is current I1t in this loop, first loop, and I22t in the second loop, and here is the output voltage we are reading at the capacitor, that is VCT. So we have to find the transfer function I2s by Vs. So I2s by Vs we have to find. This is the transfer function we have to find. So we already know that for an electrical system, the capacitor has impedance 1 by Cs, resistor has impedance R, and inductor has impedance Ls. So we can convert the circuit to an equivalent impedance circuit. So let's convert this. So here is Vs, this is R1, R2, this is Ls, this is 1 by Cs, and here is Vcs. Here is I1s and this is I2s. So now we will apply the again this impedance law to find the transfer function. So first we write the equation of motion in S domain. So here we have sum of, so for mesh 1 sum of impedance around mesh 1. So this is mesh 1 and mesh 2. Let us say this is mesh 1 and this is mesh 2. Into I1s minus sum of impedances common to the two meshes into I2s equal to sum of applied voltage about mesh 1 So we can see that sum of impedance around mesh 1. So what is the impedance here? R1 and Ls. So in this mesh 1 there is impedance R1 and Ls. So R1 plus Ls into I1s minus sum of impedance common to the two meshes. So here this inductor is common to the two meshes because this is in mesh 1 as well as also in mesh 2. So this minus Ls into I2s equal to sum of applied voltages around mesh 1. So that is we apply here Vt or here Vs in this mesh 1. So equal to Vs. This is equation number 1. Now for mesh 2 we can write sum of impedance around mesh 2 into I2s minus sum of impedances common to the two meshes into I1s equal to sum of applied voltage around mesh 2. So sum of impedance around mesh 2 is R2 plus 1 by Cs plus Ls. Into I2s minus sum of impedance common to the two meshes, that is Ls into I1s, and the sum of applied voltage around mesh 2. So, about mesh 2 there is no any applied voltage. So, it is 0. This VCS is the measured voltage. This is we are going to measure. This is not some applied voltage. So, now we can find I2S. So, again this we can apply Kramer's rule, because this is A1 x1 plus A2 x2 equal to B1, and here let us say C1 x1 plus C2 x2 equal to B2. So, we can apply Kramer's rule. So, I2S equal to, so we are going to find I2S. So, we have R1 plus Ls and here minus Ls, and this is Vs and 0 upon the determinant R1 plus Ls minus Ls, and this minus Ls R2 plus 1 by Cs plus Ls. So, this is 0 plus Ls into Vs. So, this is equal to Ls into Vs upon delta. Let us say this is delta. So, we can find the transfer function I2S by Vs. So, I2S by Vs is Ls by delta, where delta is given with this determinant. When we solve this, we will find LCS square upon R1 plus R2 LCS square plus R1 R2 C plus L S plus R1. So, this is the final transfer function I2S by Vs. So, here we saw that these two examples are taken from the reference books Norman S. Nice, Control Systems Engineering. So, here we saw that by using the impedance method, we can directly write the equations of motion in complex frequency domain or S domain, and we can find very easily the transfer function of a system. Here we saw the two examples, one of the mechanical system and electrical system. So, here I stop and I see you in next lecture. Thanks.